Got it.
Good morning, everybody.
Morning.
Happy New Year. Welcome. I'm Tracy Sprower from Met How at Home, and we're so fortunate that Dana has chosen to do another series for us here about our larger home that we live in. So, in that way, I think Met How at Home really benefits. You keep our brains going, Dana. We learn more about the land that we are blessed to be able to inhabit. A lot of folks are coming in from other places too, so welcome. And without any further ado, I'm going to hand it over to you, Dana Vasali, to go ahead and do a short introduction of yourself. And thanks so much for sharing with us.
Thank you, Tracy. Thank you, everybody, for showing up on this illustrious morning. Another great day in the Met How. Um, so, yes, my name's Dana Vasali, and I've lived in the Met How for more years than I'm willing to admit, and always been interested in the natural world. I think I even remember a book when I was a very young boy in San Francisco, Science in Your Own Backyard. And it was a book you would crawl around on your hands and knees and look for signs of nature in San Francisco, which there are plenty, of course. So it's been meaningful for me to learn what I can about the natural history of where I live, which is actually on planet Earth, but more immediately in the Meta Valley. So this is a story. This is actually a five-part story. Hopefully, I will all survive the five. Not five today, one part today, geology. But the next one is on the flora, plants of the Met How, and I do it in an evolutionary context. How the evolution of plants, and then animals, evolution of animals, and then I think I threatened to do ecology and humanity. So I have material on that. It's just challenging to put that material together in a meaningful way, but I'll give it a shot in the coming weeks. Today we're talking about geology, and it's complicated. The slideshow is not so complicated, but the story is surprisingly intricate. So this particular picture, I just looked through my pictures of the Met How Valley and one different picture from the last slideshow. And I thought that it's not as showy as some, but this is a rock glacier. So that pile of rocks in the sort of flowing down the hill actually is an ice. Is an ice glacier under those rocks, and it's left over from the Pleistocene Ice Age. And we have a very few glaciers like that in the Met How Valley, and it got covered by rocks peeling off of those cliffs, and that's insulated the ice. I don't know how far down it is. I'd guess 10 feet or more, but ice being plastic continues to move down the hill, and so you get this shape of flowing rocks. It's quite impressive. So this is near Hoodoo Pass. Hoodoo Pass, I think you can probably see my cursor here. Hoodoo Pass is on the right on the other side of this cliff. This is Buttermilk down in here that you would hike up to get to Hoodoo. So you can hike up to this ridge actually and look down on it. That's pretty easy to do from Hoodoo. Anyhow, it's just a little taste of the geology of the Met How Valley and the fact that we still have the Pleistocene Ice Age with us. So many of you might know this book, A Short History of Nearly Everything. The title's pretty small. Barson's name's awfully big there. A Short History of Nearly Everything. I'm not really recommending books per se, but this is a book I've enjoyed. And the beauty of the book is that he talks about how our understanding of the planet has evolved over time and what a difficult journey it's been. It's always been resisted. Every insight into the reality of the planet has been resisted by various human forces, like the Catholic Church, just for instance, uh, because for reasons that we'll go into, and that the short story is that there's a basic self center to human awareness And we have a tendency to think we're at the center. And the suggestions that science has offered that we are not at the center have been difficult for humanity to accept. So what Bryson's story is basically a big history story. Big history is now an academic subject taught in colleges. They teach it at Liberty Bell High School. Big history is just evolution, but it's evolution put together in a way that is continuous, so that you see that there's something going on, that there's a storyline here of, for one thing, increasing complexity. I mean, there was no planet, there was no life. All these things have evolved. Life seems to have appeared only once on the planet. That's be the scientific assessment. It only appeared once. Well, now there's, I actually forget, I think 20 million species. So it's complexification of even the planet itself has complexified over time. So that's big history. And a little plug for the Met How Naturalist. If you don't subscribe, Met How Naturalist likes these subjects. So this is, I think, the summer issue. And that picture is a BIF, a banded iron formation. It's iron strata, but it was created by iron reacting with oxygen. Well, it was life that put the oxygen in the atmosphere. So you could suggest at least, sorry, that life created that rock strata by pumping this reactive element, oxygen, into the atmosphere, which then got into the sea, the ocean, where iron particles were, and created iron oxides, which then precipitated out. So life affects the land. Land doesn't just affect the life. Well, we've had to learn everything we know. What's that saying? It ain't what you know that causes trouble. It's what you know that ain't so. So it's hard to be sure about the facts of life, but at least some things we've consolidated. So this is a picture of the Earth from the first century before the Common Era. So 100 BC, before Christ. Now they call it before the Common Era. Well, in the center there is the Mediterranean. It says Mare Mediterranean right there. Sea Mediterranean. Mediterranean. So this is their world at that time. Well, Mediterranean means the center of the earth because people have tended to feel that they are the center of the earth. It's natural, but it might be contraindicated. It might not be that healthy. I think we're the center of the earth. It might be something we learn about. It can grow out of. Another map of the world. This is obviously 1,400 years later, and more landmass had appeared. This is a European point of view, I should add. There's no America on this map. Well, there were people in America, but they weren't making maps of their continent. But the Europeans were. So they had part of Africa showing up, they had Asia showing up. The point is just that our knowledge of the world has definitely evolved over time, still evolving. So much to know about our planet. So here's a current world map with most of the countries colored in. I put it in there just because these are all the dynamic of identity. It's of such a powerful force in the human species to want to know where we're anchored. Who are we? Where do we come from? What's our storyline? But if you look at a picture of the Earth, there's no divisions. All there is land and water. That's it. So all those lines have been created by the human mind. And they're really just a byproduct of thought. Really, I bring it up mostly because of the trauma on the planet right now, because of these battles going on by people who identify in a certain way, in a certain storyline. The storyline tends to have historical background, but the history is garbled. The human history that we cling to is often highly inaccurate. It's even mythological. So that's not the main thrust of this story. We're talking about geology, but I wanted to mention that as we inhabit the planet. Well, here's more self-centered. Here's a concept of the Earth from, I'd say, the 1300s. we thought the Earth was at the center of the universe, and the stars were little holes in the sky on the outer in the outer shell. Things were in shells, and when it was suggested by people like Giordano Bruno, and I can't quite remember his years. I have it here, but I hate to look at my notes. 1300s, 1400s. The Catholic Church was outraged because for some reason the Catholic Church needed to have the Earth at the center of the universe, and the Church then at the center of the Earth, of course, center of importance. It's just a reflection of this, I would say, biological drive to survive, actually, and thereby and have importance to keep yourself alive. So Bruno was quite a guy, Giordano Bruno, and he claimed that the Earth was not the center of the universe, and the church burned him alive. But look at how intelligent he was. What a great statement he made. Truth does not change because it is or is not believed. The truth is the truth. It's a wonderful statement of reality. So this is just a reflection on the difficult journey that humanity has been on. We remember Galileo. He was he claimed that also he could tell because he was able to build a telescope. He was sure that it was a heliocentric universe, and the church was just outraged. I guess he was famous enough they didn't kill him, but he was sentenced to house arrest. So this is a kind of thing humanity constantly has gone through. This comes up elsewhere. You know, when it was suggested that the continents might move, the people who suggested it were ridiculed. How could continents ever move? I put this in just as the fact that the witch burnings. I put it in as another example of the how twisted the human mind gets and how it just fabricates what it thinks is reality. 400,000 females, mostly females, few males, were burned, killed in this 250-year period because society was sure they were witches. And here's a picture of witches that shows they actually do exist, which is just a joke, but I found that picture online. So, how do our minds work? I think is a question. Are we vulnerable? Are we vulnerable to inaccurate assessment of the planet? I think most of you here would understand that we're all vulnerable to um, misperception and misjudgments. But this little game that I'm going to show here has the potential to illustrate that. It works for some people and not others. So what I want you to do is just read this card to yourself when I bring it up. Read that card to yourself. Now, I've done this in a group. I won't do it here, but well, I can do it. You don't have to raise your hand. But if you think it says you will pick the red card, raise your hand. Well, it does not say you will pick the red card, but most people think that it does say that. But what it says is you will pick the red card. There's two thes. And most often people do not see the second the because it's useless to us. We don't need a second the. So our minds just erase it. It's visible to our eyes, but the mind interprets the world in a way that either makes sense to it or fits with its conditioning. And that's been the human problem as we've tried to come to understand the planet. So it says this is the Milky Way galaxy taken from outside the galaxy. It's a joke because we cannot get outside of our galaxy. The Milky Way galaxy is 100,000 light years across. That's light traveling at how fast? I forget, 56,000 miles per second or something like that. And it's probably the Andromeda galaxy because you can't take a picture. We can't take a picture of the Milky Way galaxy because we're in the middle of it. But we do live in a spiral galaxy. Well, we didn't know there were galaxies for quite a while, but then we thought, well, we live in a galaxy. We'll accept that. It's a little disturbing. But then in about 1924, we found out that there were at least hundreds of galaxies. And now it's thought that there's more than 1 trillion galaxies. This has all been very difficult for the human mind to adjust to because there's this urge to be at the center. And all these things have taken us out of the center of the universe. The age of the earth has been a struggle to figure out, and the church came up with its own calculation, and the church came up with a calculation by counting the begats in the Old Testament. This Bishop Ussher did that in the 1600s, and he came up with an age of the earth of 4,000 years, 4,000, BC, 4,004 BC. I think he even had a date and a day and maybe a time. He was quite precise, but obviously he wasn't right. It was based on a myth. It was based on a mythological story. Well, how are we going to figure out how old the Earth is? Well, it hasn't been easy, and there have been many estimations through time. As, say, the human mind started to turn towards science and tried to acquire evidence for making claims about anything on the planet, it wanted evidence. It looked for evidence. So here, this guy, Comte de Buffon, had a concept that he could somehow assess how long it would take for the Earth to cool, as cool as it was. Well, I don't quite understand that because I don't know how he knew it was not cool previously. But in any case, he made an estimation and he came up with 75,000 years old. Well, that was heresy. Not 4,000, not 6,000 years old, but 75,000 years old. So the current thinking, which is based on radioactive decay, and that is something that was discovered in the early 1900s, that there are radioactive elements and they have a very precise decay rate, and you can assess from the remains of certain radioactive elements, their current condition, when they were formed, you can actually assess the age of those elements and thereby assess the age of the Earth. And the current widely accepted age is 4.5 billion years. So we've come a long ways from 6,000 years to 4.5 billion years. All these things had to be figured out. So on the upper left there, this fellow who I sounds so Italian, but I guess he's French. He noticed that he was one of the first to draw a map of the fact that it looks like the continents fit together, and they do fit together awfully well. South America, Africa, North America, Europe, they fit together quite well. So this idea was coming out in the 1800s, drawing this map. And then, not too long after that, actually, Alfred Wegener came along in the early 1900s and was able to offer evidence that the planets had been joined together. I might be the next slide here. Where do we go? Yeah, this would be so. This is information that Wegener was able to ferret out by field work, and he found that there were fossils shared across the continents. That Africa and South America shared common continents, common fossils, and the other continents as is drawn in there. So it was some kind of evidence that the continents had moved, that they had indeed once been together and had split apart. He could not come up with a mechanism. How could you move a continent? How could that be? Well, that's information that has evolved since Wegener's time. I think he died in about 1932 on an expedition in Greenland. Looking at, yeah, that's right. Yeah, expedition in Greenland. He froze to death. But science went on, the scientific inquiry went on, and in the 50s, several things emerged about the ocean. One is that there was a ridge down the middle of the Atlantic and also a ridge in the Pacific, but the one in the Atlantic is right down the middle of the ocean. But also they were able to start assessing the age of the ocean floor, the ocean plates. And you know, if the Earth is 4.5 billion years old, you'd think the ocean plates would be 4.5 billion years old. Well, the oldest ocean plates, let's see if I have it here, is 200 million years old. And the oldest plates are at the perimeter up against the continents. And the youngest plates are at those mid-oceanic rifts where some are brand new. So this is part of the scientific inquiry that led to the understanding that something is moving the continents, and that the ocean plates are disappearing. They're being pushed up against the continent, and they're going under the continents. They're subducting. Meanwhile, new magma is constantly coming out at the mid-oceanic plates, like that. But the point is that we had to figure all this out. The humanity,
Your track dropped a little.
I mean, I denigrated the hunger for identity that creates the separation in the human species, but you have to admire the inquisitive, powerful, inquisitive nature of the human mind. So this is a mid-oceanic ridge. There is one of these ridges down the middle of the Atlantic, and there's constantly magma pouring out. It cools, and it pushes the cooled magma to the east and the west. So this is a little complicated, but what we just established is that there's a cycle going on with fresh magma constantly coming out from the center of the Earth, being pushed east and west, and then we haven't really gone into it, but that magma, as it's cooled, it gets heavier from cooling and subducts under the continents and goes back into the mantle, and then is cycled back out at the mid-oceanic ridge. So this cycle, I don't know if I left that. I took that one little cycle. Well, the interesting thing is every time that these rocks cycle through the lower crust and the mantle, they're altered slightly because different minerals might solidify at different temperatures. So the minerals that solidify from liquid to solid at the lowest temperature will migrate out first. And as you cycle these rocks, you get more and more of the minerals that cycle out that solidify at cold temperatures, like granite. And what that has led to is an increase in continental landmass over time. The continents are made out of a different kind of rock than the ocean crust. There's continental crust, there's ocean crust, but they're different. Continental crust has more silicaceous rock, more silica. It has less mass than more dense rocks that have iron and magnesium in them. And so the continents end up floating on the ocean crust, and they have increased over time because of this cycling of rocks over time. So this continents have actually evolved over time greatly. Another point of interest is that the moon, it's well established that it's agreed upon in the scientific community that the moon was created by a collision of the Earth with a smaller planet called a planetesimal, just means a small planet, that reheated the Earth, caused more of the heavy elements to sink towards the Earth's core, like iron and magnesium, and blew some of the Earth's crust out into space, a lot of which went into orbit around ran into orbit around the Earth, and then accreted into the moon. So this collision created the moon. So I think so. It says here a catastrophic, massively destructive. There was no life on the planet, or it would have killed everything. Supremely beneficial collision. Why would this collision be beneficial? It's claimed by many. So that's a picture of the smaller planet hitting the Earth, and then the debris going into orbit around the Earth and then accreting into this moon. It's now thought that if there were no moon, there might be no life on the planet. That this catastrophic collision made life possible on Earth. And why is that? Well, the moon stabilizes the Earth orbit. Because of its gravity, it stabilizes the Earth orbit. If the Earth wobbled more, and the Earth does wobble a little bit as it moves around the sun, if it wobbled more, it would create more dynamic weather patterns, which would be much harder for life to withstand on the planet. It's hard enough to withstand hurricanes as it is. Also, the moon creates the tides, and tides create variability over time, washing nutrients back and forth, and have greatly increased the diversity of life on the planet. So this is what a term you've heard, I'm sure, called the Goldilocks effects. that there are, I mean, I've got a list going in my big history file of Goldilocks effects, and I forget, there's got to be at least 50 on the list, on my list, and there must be hundreds of coincidences, these Goldilocks effects that seem random, but have made life as rich as it is on the planet. I think, oh yeah. So I just pulled up a issue of the Met How Naturalist because the naturalist likes this kind of stuff. So there was an issue. What if there were no moon? Well, if there were no moon, it's highly possible there would be no life on Earth, and it came from a catastrophic collision. It's paradoxical, profoundly paradoxical. I put this in at the last minute because we're going into a little more geology, but I realized that the atmosphere is part of the planet, and it's a critical part of the planet, and it also makes life, it's affected by life, and it also makes life possible in ways that we know. It blocks out some of the cosmic radiation that would break up our organic cells and even our DNA. So a nod here to the atmosphere. The atmosphere is 78% nitrogen. It's 21% oxygen. So it's mostly nitrogen and oxygen. That's all put in the atmosphere by life. So so life has created the atmosphere by and
Up here, I
large.
said,
There's a little bit of carbon
pond or wetland down to our left, maybe a quarter mile.
I can't quite see your name, Tom. Oh, you made a comment. Well, I didn't quite get it, but you might be disagreeing, but that's fine. Um, Anyhow, life has to a large extent created the atmosphere. Oxygen is highly reactive. It would not be in the atmosphere if it were not constantly pumped into the atmosphere through the process of photosynthesis. See what else we got here. So this is oxygen in the atmosphere. Over time, that graph starts with a million years ago on the lower left and goes to the present. Well, a billion years ago, there was very little oxygen on the planet because there wasn't that much photosynthesis occurring. Oxygen has been pumped into the atmosphere by photosynthesis, both by photosynthesizers in the ocean and by land plants, and it went up to 35%. I mean, it's thought. There's evidence that it went up to 35%. Well, the problem with a high level of oxygen in the atmosphere is that fires burn much more readily, and it's hard to have organic matter on the planet if you have 35% oxygen. Anyhow, it has leveled out a while ago and is now about 21% oxygen. So Goldilocks effects, everything is just right in the strangest ways for life on Earth, including the Earth is in just the right place in the distance from the sun to be an habitable zone where water can exist as a liquid and a solid and a gas. And that's not true for any other planet. So we live in the Goldilocks zone. So this might seem, we're going to get to geology, I swear. And this might seem a little obtuse, but it's easy to understand the basics. Like here's a hydrogen atom. Hydrogen has one proton and one electron. So you can accept that. We don't know how that was created by the dynamics of the universe, but that's the way it is. But that shell, that electron shell, that orbital, holds two electrons. I meant to try and understand, and somebody here might know that, but we don't have time to go into it. But for some reason, the first electron shell holds two electrons, while hydrogen only has one. There is a proclivity, a desire, I mean, put that in quotes, that's anthropomorphic, an electronic urge for hydrogen to fill its one electron shell with one more electron. And so it readily joins together with other atoms to share an electron and fill that electron shell. These are electron shells. So S1 in the middle there, this first electron shell holds two electrons. Second shell holds 8. Third shell holds 8. Fourth shell holds 8. So hydrogen will join with itself. You get H2. I think it probably mostly exists in the atmosphere. If it's free hydrogen, it's going to join with other hydrogen and form a molecule and share electrons and the electron shells will be full. It's just a force in the universe, especially on the planet, for the shells to be filled. So here's that same hydrogen sharing 2 electrons. Well, here's oxygen. It has it has 8 electrons. The first 2 go in the first shell and fill the first shell. The remaining 6 go in the second shell, but the second shell holds 8. So in an electronic sense, it wants 2 more electrons. Well, what if you shared 2 hydrogens? If they shared their 1 electron with the second electron shell and oxygen, what would you get? You would get water. The point is the complexification of elemental life in the universe built into the structure of the universe. It's just built in to. So silicon has 14 electrons. Second shell has 4 electrons. It wants 8. It wants the electron shell. So it could join together with oxygen, which has 6 but wants 8 in this way, and it forms quartz. So quartz is, you could say, an inevitable product of the structure, the elemental structure of the universe. It's bound to evolve where these elements exist. So the periodic table is based on these electron shells. So I wrote in there up at the top, upside down, it says these are missing 2 electrons. Remember oxygen? It wants 2 more electrons. Below that is sulfur, missing 2 electrons. Probably selenium, missing 2 electrons. But that's how this chart is put together. I pulled up over there on the far right there in red, those elements, those electron shells are full. They don't react with other elements. But that's not true for any of the other elements. The fluoride, is that fluoride and chlorine, missing one electron. They are going to join with other elements that can fill that electron shell. Over on the left, missing 6 electrons. The point here is this incredible orderliness of the periodic table of elements, of the elements that exist. They have this orderly quality and this tendency to join with other elements and create greater complexity over time. So this great statement by this Nobel laureate, Kristin Debud, there's no shortage of ordered self-assembly in the universe. He says this urge is so powerful that life may be inevitable. And I like at the bottom, an obligatory manifestation of matter. Now that might not be true. He is a Nobel laureate in chemistry, but you see that there's this propensity for the universe to grow more complex over time, probably most especially on Earth. Good planets are hard to find. So this is a volcano. I think it's in Indonesia. The crust is 7,000 degrees. The core is 10,000 degrees. Why? Why is the center of the Earth molten? The answer is radioactivity. We're going to talk about that. So these are elements. And the scientific story is that the only elements that existed in the universe after the so-called Big Bang, which fortunately we don't need to talk about, were hydrogen and helium. Hydrogen with 1 proton and helium with 2 protons. And all of the other elements on that periodic table, forget exactly how many, 112, 15, 117, they've all been created over time, mostly in the center of stars. Like these the oxygen, carbon, nitrogen were created in red giant stars. The other elements in blue were created in hot blue stars. There's so much heat and pressure that the smaller elements were pressed together so that if you had 1 proton, if hydrogen joined with helium, you'd have 3 protons and you'd probably be lithium. So the elements have evolved over time. They didn't exist And this evolution went as far as iron down there at the bottom, Fe, iron, ferrous, 26 protons in the nucleus. And I guess this process stopped there. I forget exactly why, except that that's all with the heat and pressure in these stars. That's as far as the process could get. But then there have been supernova explosions where stars collapse on themselves and the heat and pressure increases exponentially. And it created elements which have so many protons in the nucleus, they can't hold themselves together. They're radioactive down at the bottom in red, radium, radon, and uranium. Uranium at the bottom, 92 protons. They're all positively charged. They all repel one another. Uranium can't hold itself together. It decays spontaneously and it gives off energy. So I put a little energy arrow in there. Well, somehow in the Earth's core and in the mantle, there are radioactive elements that are decaying over time and giving off energy. And that is where the heat of the center of the Earth comes from. This is a great artist concept of what the Earth would look like if you sliced it in half. So you've got these convection currents rising because of this heat. The hotter temperatures in the core rising through the mantle and creating these uprising convective currents that actually split the Earth's crust open in places. We call it either volcanoes or the mid-oceanic rift. So here's our volcanoes, St. Helens. So these numbers are cubic miles of volcanic debris that came out of the volcano. It's a little hard to see it, but I can see Mount St. Helens spewed out 1 cubic mile. If many of us remember when that occurred and the chaos that ensued with 1 cubic mile of volcanic debris spewed out. Toba, 75,000 years ago, spewed out 2,800 cubic miles of volcanic debris. And it's not on this chart, but a notable event in the history of North America is the explosion of the Yellowstone caldera. I'm trying to remember, it might have been 50 million years ago. That was 250 cubic miles. So far less than cubic miles of volcanic debris came out of Yellowstone. I think it was 50 million years ago. Far less than Toba, far more than St. Helens here, which was 1. And reading in the kind of thing you find in a short history of nearly everything, there was up to 2 feet of volcanic ash in Nebraska, 1,500 miles away from the explosion of the Yellowstone caldera. So we live on a fairly dramatic planet. Here's our volcanoes down the Ring of Fire, so-called Ring of Fire down the Pacific coast. This shows how often they have gone off in the last 4,000 years. The most active volcano is St. Helens. It's not that safe to live adjacent to a volcano. And Rainier is no slouch. Where's Rainier? There, here. Rainier. Well, Rainier has erupted. It has 4 here. There may be another one hiding behind our picture. So we end up with this dynamic Earth crust with magma pouring out at the mid-oceanic ridge, which I just put an arrow to the mid-oceanic ridge. It comes out under the ocean. It cools. It's pushed by the continual outflow of magma. It's pushed east and west. It reaches the Earth, the continental crust. It's heavier than the Earth's continental crust, and it subducts under the crust. It goes down. It remelts, and eventually cycles back out again. So the Earth actually recycles itself, astonishingly. So the reason we go into all this is because this is basically the history of the Methow Valley, which is what we're supposed to be talking about. This is a diagram of plate tectonics and subduction. Here's an ocean plate here. It's subducting under a continental plate. It has a fragment of continental plate called a terrain stuck on the ocean plate, and the terrain moves with the ocean plate. This plate is subducting. This terrain is going to reach the continental plate and is going to get scraped off. the continental plate and accreted onto the continental plate. An example of that is the Farallon Islands off the coast of San Francisco. They're moving at some rate of speed. I think it's a centimeter a year. The crust often it's said, probably somewhat accurately, they move about as fast as our fingernails grow. So it's slow, but it's steady. And Earth has plenty of time. And so these dynamics are constantly occurring. So here's our terrain, ocean plate, eroding continent. That's very relevant to our story. The continent's constantly eroding sediments off into the ocean, which are accumulating there. And you end up, as the terrain is accreted, jammed onto the continent, it deforms the sedimentary rock that had accumulated off the coast of the continent. It deforms it and crushes it in one direction or another, often upwards. And that is the story of the Methow Valley. Methow Valley is full of sedimentary rock, which is a lot of it is oceanic with ocean fossils in it that is deformed. And a lot of times it's like 80 degrees, almost 90 degrees straight up. So these are terrains. All these multicolored fragments are terrains that have accreted onto the North American coast over the last, I forget, 500 million years or something like that. But this is the history of the North American coast. It's not a minor element. Meanwhile, we have this process going on of the evolution of the rocks because they're heating and cooling. They're heating to molten and then cooling and then heating again and cooling, and different elements migrate out at different temperatures. So we end up with a multitude of igneous rocks, not just igneous rocks, but a multitude of kinds, metamorphic rocks, various kinds of metamorphic rocks, and then they are worn down into sedimentary rocks. But it's so this, you can't see it very well. You can get your hands on this either at the Methow Natural Store. I can email it to you if you want it. But this is a stratigraphic column of the Methow Valley. So up here is Pipestone Canyon. You can almost see it. Midnight Peak Formation, Ventura, Winthrop Sandstone, Twist Formation down at the bottom. Many of these are sedimentary, and many of them have marine fossils in them. So this is the history of the evolution of the Methow Valley. I circled here Pipestone Canyon. It is, do I have this thing right here? I do. It has a thickness, and the thicknesses are shocking. That says 2,500 feet. Pipestone Canyon has 2,500 feet of sedimentary rock. So Pipestone Canyon has fossils in it, but they're not marine fossils. They're terrestrial fossils. It may come up here later, but it has dawn redwood fossils in it from 65 million years ago, quite close to the time that an asteroid struck the Earth. It's widely agreed in the scientific community and killed off the dinosaurs. Paleontologists have come to Pipestone looking for dinosaur fossils and never found any. This is a geologic map of the Methow based on that stratigraphic column and based on the work of the original geologist in the valley. What was his name? And this is available. It costs a fair amount to print this. It's big and on plastic. I have one on the wall over here. But you can get it for $25 if you want one. You'd have to let me know. This was done by Ron Bomba. Thank you, Ron, for putting that together. Here's an X. This is Twisp. Here's an X. This is Winthrop, just to get you oriented. I think I circled the Chewok River here. And these are all mostly sedimentary strata. And an interesting thing about these strata is they show up on both sides. This is the Methow River. This green is alluvial fill along the river, but the same strata shows up on both sides of the river because the Methow Valley sank downwards due to the forces of plate tectonics, like this. These are the various strata shown in cross section. This is Midnight Peak. K stands for Cretaceous, Midnight Peak. This is the Winthrop Sandstone. By the way, the Winthrop Sandstone shows up in two places. It shows up, well, I have a picture of this coming up here. Twist Formation, Harts Pass Formation, Winthrop Sandstone. So why are there marine sediments at the bottom here, 100 miles from the ocean? And why are they crushed? Well, we've kind of talked about why they're crushed. The reason there are marine sediments is the Medhow used to be a shallow sea. And as terrains accumulated to the west of us, it pushed the land upward and crushed it and created the landforms that we know today. And here you can see it. This is the Twist Formation. And while this is so dramatic, the fact of the matter is we who live in the Medhow drive by this at least once a week because this is near the Winthrop Post Office. If you leave the Winthrop Post Office heading towards Twisp, you go up to the top of that first hill, and these marine strata are displayed there, but you can't slow down. Everybody's going 60 miles an hour, and if you stop, you'll be killed. But they're beautiful. They're just magnificent. So that's where that is, and you can stop and get up on a little knoll across from it and look over at it. That's why I took this picture. But this shows you this is marine strata laid down horizontally and now pointing up almost 90 degrees, and that's not uncommon. Hart's Pass Formation. This is the strata. Again, at about 80 degrees, crushed by the forces of plate tectonics as terrains moved in and plutons moved in west of the Medhow. Here's Virginian Ridge. Look at the strata, 80 degrees, very common. This is also Virginian Ridge. This is at Cache Creek up on the Hart's Pass Road. If you stop, park at Cache Creek and hike up the creek, there's a bit of a jumble of debris. You see these remarkable structures where this strata has just been melted, crushed, the forces of plate tectonics at work. More strata. This is Winthrop Sandstone. This is at Dripping Springs. You can probably see it from the parking lot of Dripping Springs. But the same strata, surprisingly, this is on Twist River Road. This is also Winthrop Sandstone. This is coal down here. It's full of organic matter. It doesn't burn. It's low-grade coal, but it is full of organic matter. So let's see, Ian Miller, who grew up on Squaw Creek, now has a new name. I forget the new name. Did his PhD on the Winthrop Sandstone, and he found 135 different vascular plant fossils in the Winthrop Sandstone. He went up here at Dripping Springs with his family and a crowbar and started prying these rocks apart. And he found these most magnificent fossils from, can't remember. Let's see, do I have the age here? 100 million years ago. 100 million years ago, these fossils were laid down and then went through the geologic process of being crushed by plate tectonics and terrains moving in from the west and pushing it up again at about 85 degrees. More strata. So I think some of this is volcanic strata, would have also been laid down horizontally. This is midnight, but you can see the strata here. This is up at almost 90 degrees, again from the forces of plate tectonics. Pipestone this is a Dawn redwood that I found some years ago in the sandstone of Pipestone. A lot of Pipestone is cobblestone deposits, but there are layers of sandstone and they're fossil bearing. 65 million, let's just 60 to 65 million years ago. Well, the story never ends. And so after all this drama of strata being laid down and being crushed by plate tectonics and terrains moving in, there have been repeated ice ages over the last 2 million years. There are estimated 20 glacial advances in the Pleistocene over the last 2 million years. This is an artist concept of the last ice age, which extended. There was these are ice sheets. Forget the name. Cordilleran, and anyhow, there may have been a land passage for part of the time of the last ice age. There was land passage down from Alaska. But the point is that there's a lot of variation on the planet, and this ice covered the Medhow Valley. This is a picture, I like to say, this is a picture that I took of Gardner and Silver Star 16,000 years ago. Not true, but this is what it would have looked like. only the tops of Gardner and Silver Star. That's all that projected out of the ice just 16,000 years ago. And so much of the landscape of the Meha Valley, the central picture, is created by ice. These terraces are came terraces created by water that was melting off the glaciers and washing debris off to the edge of the glacier. The whole middle of the valley was full of ice, but the ice melted over time, stepwise, and so there are lower terraces, terrace here, terrace here. You can see these terraces in the valley. There are these rocks that are rounded by water scattered all over the valley, but there's no water. They're out in the fields and meadows. They're glacial erratics that were dropped there by the glacier when the glacier melted. So all this evidence that had to be interpreted by the human mind, which puts itself to useful work at least occasionally, has figured all this out over time and in fairly recent time. You know, it was the ice ages were not accepted until the early 1900s. I think even later than that, it might have been the 1850s or 1950s that was accepted that these huge glaciers came down during the Pleistocene Ice Age. This is a little difficult to see. I circled Winthrop just to locate you. These are coulees, and coulees. Well, coulees are temporary water courses like a river, but a temporary river that flowed for a while and then stopped as the ice melted. I circle Pipestone Canyon here because Pipestone Canyon is a coulee. And what happened with Pipestone Canyon is water coming down the Chewok, which would have been here. This would be the Chewok. This is the Methow. The water coming down the Chewok as the glaciers melted, say 15,000, 12,000 years ago, the valley was blocked and the water was forced off to the east and went up Peregrine Creek and flowed down. The meltwater flowed down Pipestone for some period of time, probably a couple hundred years, and carved that canyon. And then the ice melted and the water went away, and now there's no water in Pipestone Canyon. It's a coulee. There was a different world before the Pleistocene. 2 million years ago, during the Pleistocene, and up to the end of the Pleistocene. I would put the end of the Pleistocene, I would put the ice melting, say 14, 15,000 years ago. Right in that time period, there were 75 species, at least 75 species of large mammals, I think defined as being over 5 pounds, 2 kilograms, that have since gone extinct, that have gone extinct in the last 15,000 years. There were at least 3 species of elephants in North America. There were llamas, stag elk, just innumerable creatures. I do have a list of what was here, and they all went extinct. And it's difficult to understand why. It's not fully agreed upon why that happened. But the leading theory is that humans, which migrated across the Bering Land Bridge about 15,000 years ago, and were big game hunters because there was big game in Siberia, and they'd learned to hunt the mammoths there, and they created these enormously large spearheads, which you don't need if you're killing rabbits. And these are found all over North America, these Clovis spear points. It's widely thought that these hunter-gatherers caused the extinction of many of the large mammals that no longer exist in North America. So things keep changing. It's a dramatic story. It never stops. And we are immersed in the story and have our own small time and part time to experience it and part to play. This is a nice statement by the Roman. Time is a river of passing events and strong as its current. No sooner is something brought into sight than it's swept away and another takes its place. That is the nature of our world. So I put this in almost at the last moment. What do you think your body's made out of? Life emerged from the dynamics and the elements of the planet. There is a very mysterious process going on Earth that we should not overlook. Science has not been able to explain how life emerged on the planet and our own bodies are actually made out of the elements of the earth and the atmosphere. Well worth contemplating. So here's topography of the Met How today. It won't last. It's temporary. Was covered with ice. It was an ocean floor, probably a mountaintop, and now it's a beautiful river valley that we get to enjoy, even if it's another cloudy day. So there is an in-person talk today, tonight. If anybody wants to come, it'll be this slideshow, but I'm bringing rocks. We're going to look at rocks in the lab. I'm going to show a film. You can eat dinner during the film if you bring your dinner, but if you're interested, that's happening. Met at home. Tracy videotaped this, so it'll be posted if anybody wants to see it. Met How Naturalist can always use another subscriber. If you want to contact me, that's my email. So I think that's the end of the line.
Wow. Yeah. 3 minutes to spare. That was excellent. Thank you so much. Does anybody have any questions?
Yeah. Or corrections? I would accept corrections.
You'll have to unmute or put it into the chat if anybody.
Is there any chat? I forget where chat is.
Ask. Oh, here's some of the chat comments. Absolutely fabulous program. Great start to 2024 from Melissa. Maria says, thank you so much, Dana. Ron, most excellent. Patty, awesome class. Thanks. So
yeah, thank you
guys.
guys.
Was really, yeah, thanks for swooping us to the big picture and down to the micro, to some of those scenes that we pass by.
Yeah.
It's just, yeah, it's amazing.
Yeah, it's a good story. Good to get out of ourselves and have some insight and feeling for the larger world.
Thank you, Dana. That was great.
Thank you.
Yeah.
Excellent. So for anybody who can stand more, we'll do it again next week on the evolution of plants and the evolutionary story of plants in the Met How. That's how I'm going to approach it. Okay.
Fantastic.
Thank you.
Okay.
Thank you, everybody.
Thank you.
Enjoy your day.
Super. Yeah. Thanks so much.
Thank you.
До свидания.